Hello. Hello.
Hello, sir.
Yeah, can you hear me?
Yes, sir. We can use.
Okay. Okay. Thank you.
Good evening to you all. We have now entered a world with many technological advancements. The topic technology has become intensely dynamic. We are happy to bring out and host the topics of the industry regarding power electronics, EV, and renewable energy. It's my pleasure to invite the chair of the PES student chapter of the IEEE student branch, University of Ruhuna, Mr. Akhila Avantha, to deliver the welcome speech.
Hello, Sahan, can you hear me?
Yes, sir, we can clearly hear you.
Hello, good evening, everyone. It is my pleasure to welcome you all to this webinar on power electronics today. And I would like also to extend my special welcome to our honored guest, Mr. Prashanth Atputhakumar, who is currently working as the head of the power electronics at VEGA Innovations. We are really delighted to have you all here today. And we hope that we will find the session more exciting and we'll grab a lot of information about electric vehicles related power electronics. Thank you. You are welcome, sir.
Thank you, Aya. So it's my privilege and honor to introduce our guest speaker today, Engineer Prashanth Atputhakumar. He is the head of power electronics of VEGA Innovations, which we all know delivered great glory to Mother Sri Lanka through their VEGA car. He holds an honors degree in electrical and telecommunication engineering from University of Morocco. Without further ado, Mr. Prashanth, the stage is yours.
Hello, good evening, everyone. I hope you all can hear me.
Yes, sir.
First of all, I would like to thank Power and Energy Society of University of Ruhuna for giving me this opportunity and inviting me as a guest speaker at this event. And also, it is my pleasure to speak on one of my favorite topics and about my experience in power electronics and about VEGA as well. Today's session, I have structured it as you all are more interested in car, I will talk a bit about journey about VEGA and the story behind VEGA and what we are doing now at VEGA. And then I will talk about power electronics and how it is applied in electric vehicles, renewable energy, and so on. And at the end of the presentation, I will talk about the switching devices, which is the most basic and important part of power electronics. And I talk to some extent about converters and inverters. I will not go in deep like any technical. I will just talk about important things which I feel important for you all. Today's topic is power electronics in electric vehicle and renewable energy. I will give a brief introduction about me. I did my bachelor's at University of Morocco in Department of Electronic and Telecommunication Engineering. Soon after graduating, I joined VEGA Innovations in 2017, and now I'm working as a head of power electronics, and I'm leading the teams towards power electronics projects. That's it about myself, and let's move on with the car. Okay, as you all know, this is our car. This is the photo we took in our garage. So two key persons of our organization is Harsha Subhasinghe, who is President and Chief Executive Officer of Cochin Group of Companies, and Dr. Prashanth Atputhakumar, Director and Strategic Planning. Both of them got together and developed the idea of VEGA supercar and all the other projects that's currently ongoing in VEGA. This is the timeline. Like in 2014, we started building the shape of the car using cardboards and stuff to make the structure. And we made the space frame chassis. And then in 2015, it's followed with body panels, which is made, first we made it fiberglass and then made with carbon fiber. The final is with carbon fiber. And after that, the important milestone is like motor controller. That's you can see that's one of main power electronic component in the car. You can see on right top of the right top corner. And after that, we did 0 to 100 in 3.15 seconds in 2017. And 2018, we fixed the carbon fiber body panel and interior panels and everything. And in 2019, we painted the car. And in 2020, we took it to the Geneva International Motor Show. Okay, this is where the idea of VEGA started. This is Dr. Beshan's home garage. So this is just a beginning, like this is where they started the design of the car. And this is how it came into real world, like the structure and the body plugs and carbon fiber body panel. This is actually before painting the car. This is the color of the carbon fiber materials. And this is the final product, which is launched in 2020 Geneva Motor Show. Actually, this was taken in Geneva, but due to pandemic, the launch got cancelled. So we had a virtual launch. The event got cancelled. So we had a virtual launch, which I think you might have seen in the videos. Okay, when we talk about spec of our car, its torque is 760 Newton meter and power is 804. It has an acceleration of 0 to 100 kilometer per hour in 3.1 seconds. And it has a range of 300 kilometers per charge. I'll talk briefly about the components which you can find in our vehicle. Like, first most important thing is battery pack, the prime power source. First, we developed it with LFP technology, chemistry battery. And now we have changed it to NMC. That's the development we had from our previous version. And our future development will be based on NCA chemistry, which is cylindrical cell technology. And the next most important part is motor controller. We have a motor controller developed in-house. Even the battery packs are developed in-house. Battery packs, like we bring battery cells and then we assemble it and we develop all our battery management systems in-house. So the whole battery pack is developed in-house. We have a separate team for battery. Even for motor controller, everything is done like PCB design, testing, simulation, everything is done in-house. And now we have a separate team working on motor controller as well for the future development of cars and other EVs. And then we have a digital instrument cluster, which is to display like all the other cars, speedometer, seats, gear shifts, and other important parameters, which surely you can find in instrument clusters. That's also built in-house by our engineers, especially with software engineers. We have a software team as well working on it. And then we have vehicle control unit, which is the heart of any electric vehicle, any vehicle, which controls all the operations and all. Everything is built in-house. And in addition to that, we have like thermal management controller, Like that's what maintains the thermal stability. Like we have components like motor controllers, battery packs, and other power electronics components which gets heated. So we have a thermal management system which regulates the temperature and keeps it in the possible range. And then we have our own charge controller, like our VEGA can be charged with both AC and DC charges. So we have our own charge controller. Okay. Apart from car, some of the other projects what we are doing is electric vehicle conversion. One of our main iconic product is a Mini. It's a Mini Cooper. We converted into full electric. We even changed interior panels and like outlook as well, like headlights and stuff. We changed it to custom design. And then the big product we are developing now is electric three-wheeler, which is more convenient for the urban transportation. As the cities are getting very congested, we have to find a solution with a compact transport medium. So we are developing three-wheeler now. And another product we are developing is all-terrain vehicle, which is which you all have seen in adventure sports, something like that. So we are developing it also as all electric vehicle in our development. Apart from EV, we have electric vehicle chargers as well. We have a separate company running like ChargeNet. We are the leading charging network providers in Sri Lanka. We have both fast chargers, which is a DC charger, 30 kilowatt and 50 kilowatt versions. And we have L2 chargers, which is AC charger, which is 3.3 and 6.0 kilowatt versions. And I'm happy to say that we have started exporting our chargers to India as well. And another branch is AI Grow, which is mainly focused on agriculture kind of things. Here we provide like from start to end solutions, like from building greenhouses, automating greenhouses. We have separate agronomists with our team, like giving expert advices to the clients about their plants and stuff. And we have separate software running on the background, like we have mobile apps, web applications and things. We have a fully automated fertigation system. So everything is automated and we provide start to end solution for the customers. So that's pretty much about our main projects, and we have some other projects as well going on, which is under VEGA Design Studio. Okay, let's start with today's topic. Okay, power electronics. What is power electronics? Then I came across with two interesting explanations. One is from Wikipedia. Power electronics is the application of semiconductor electronics to the conversion, control, and conversion of electric power. So, power electronics is basically based on semiconductors like MOSFETs, diodes, and stuff. So it is converting the electric power from one form to another form and controlling it. And there is another explanation from Synopsys, like power electronics is the branch of electrical engineering that deals with the processing of high voltages and currents to deliver that supports variety of needs. Okay, what they say is like, as they say, it is not necessarily to be high voltage and currents, even medium voltages, low voltages, everything comes under power electronics. So it is like processing the voltages and currents to deliver the power to our desired needs. So what is more interesting about power electronics is it has the ability to change the basic characteristic of any electric power. Like the basic things are like voltage, current, and frequency. Power electronics has the ability to change those things. Like you can change it from one voltage level to another voltage level. You can change the current requirements, and you can even change the frequencies. Like you have AC signal, AC power with some frequency, and for your requirement, you need it in another frequency. So those requirements are fulfilled by power electronics. Today we are talking about carbon neutral environment, zero waste, and everything. Everything is possible just because of power electronics. Okay, this is how basic power electronic system, like this is a summary of power electronics. You have an input power and you need an output power which is required for your equipment or your setup. And in between, you have the power converter. Like it has the ability to change the voltage levels or current levels according to your requirement. And you have a controller to control it. Like you have to regulate the output, voltage or current or even frequency. So you get the feedback from the output and check it whether it's under your requirement. And if there is any error, or you have to regulate it. And those decisions are made with algorithms, and those signals are sent to power converters. Power electronics runs around 4 main topologies for converters, inverters. Like these are the 4 basics equipments or like converters in power electronics: DC to AC converter, DC to DC converter, AC to DC, and AC to AC. I will just explain in a line or two about each of these converters. So DC to AC converter. So DC signal is something like it's constant or sometimes varies with time, but not in a periodic manner. Then you convert it into AC. For example, we can say motor controller in electric vehicle. The battery is DC source, and then you have a motor which is the load which needs AC. So that's an example for that. I'll explain it about in later slides. And it same applies for the DC-DC converter and AC-DC and AC-AC converter. So the last one, AC-AC, is like mostly they are like combination of AC to DC and DC to AC converters. Okay, application of power electronics in electric vehicle. This is the diagram which I got it from Google. It shows the basic blocks of power electronics inside an electric vehicle. So three main components are inverters, that is traction inverter. You can find it above the motor here, like there's a 3-phase motor and you have a motor drive, the motor controller. What is the use of that is, in electric vehicle, you have high voltage batteries, like usually the passenger vehicles will come around 400 plus voltages of battery pack. But the motors, the load is AC. You need to convert the DC power source into an AC power source. So that is just like an engine in a fuel vehicle. That conversion is done by traction inverter, which is the most important part of any electric vehicle. And yeah, this is the what you can see in the bottom right corner is our motor controller, which is developed in VEGA. Even the enclosures are developed and designed in VEGA. The next thing is DC-DC converter. This one you can find like in two places, like you can check it like here you have 12 or 48 volt battery on the right top corner of the photo. So in normal vehicles, you find alternators to charge those batteries. In electric vehicles, you have DC-DC converter. You have high voltage battery, which is the main power source. Even when you are charging the electric vehicle using charging stations, those high voltage batteries are charged primarily. So you need to charge the low voltage battery, which is used for other auxiliary requirements like headlights, horn, and wiper. All the stuffs work on low voltage. So you need to charge that small batteries as well. So there we have a Dc2 Dc converter, which converts high voltage DC power like from battery and to charge the low voltage batteries. Nowadays, you have 48 volt batteries as well. The advantage of 48 volt batteries is like you don't need complex cabling, like you don't need the cables to pass the current. You can manage the wire harness very easily with 48 volt batteries. Still, there are 12 volt systems, but in the future they are going towards 48 volt battery systems. Okay, then we have an onboard charger. Just like your mobile phones or laptop, you need to charge the battery inside the car as well. But what's the difference is like we have two kind of chargers. One is AC charger and another one is DC charger. So when you provide the AC power, it has to be converted into a DC power to charge the batteries. So when you want to like charge your car in the home socket or something, then you need to have charging circuit inside that car. That is what we call onboard charger. And also sometimes nowadays it is kind of bi-directional. Like when there is no power in the grid, it can reverse supply the power, like from car's battery, you can power it to the grid. Those are future technologies. Even some manufacturers has already developed that. We have even that technology in onboard chargers in future of vehicle. Okay, apart from EV, even for vehicle chargers, we need power electronics. Like in this table, they have included four kinds of charging. First three are like AC charging. Those kind of stuff I explained earlier. Like you give AC power and you have a converter inside the car. Using that, the car battery packs are charged. And the fourth one is the most interesting one, and that is where the power electronics come in charging technologies. Just like laptop adapters and phone charging adapters, this DC charger converts all the AC to DC and provides what is needed by the car. So it delivers DC power directly to the battery. So it is kind of fast charging and it can deliver high power. And in addition, even in the AC charging, we have a communication running in between charges, like when to start charging, what's the current requirement of the battery numbers, kind of stuff are exchanged between vehicles. So even in charging technologies, power electronics is applied in DC chargers. Apart from that, now there are developments going on for wireless charging, inductive charging. Those are the developments that's going in vehicle charging technologies. Even there are chargers like which takes power not from the grid, just straight from the solar. They convert it directly into DC and supply it to the electric vehicle. So it is kind of, you don't need any fuel there, like you are not getting the power from the grid. So it is purely carbon neutral power source. That's it. That's the brief summary about power electronics in EV. Then I will talk a bit about renewable energy. Okay, when we talk about renewable energy, the main source we come across is solar. I will talk more on solar inverters and solar stuffs, and also we have wind energy and even waves energy. So there are some other renewable energy as well. Main sources are like wind and solar energy. So in wind converters, what you do is, what wind turbine generates is a variable AC power, which is not used directly into the grid. Like you can't feed that AC power directly to the grid because of varying power levels and even frequencies. So first what they do is convert it into a DC and then convert back into AC, which is utilizable by the grid. Same applies with the solar panel. The only difference is solar is generating DC power. So first you have a DC-DC converter and then you have a DC2 AC inverter, which converts the power which is usable by the grid. Okay, most available inverters in the markets are string inverters, central inverters, micro inverters, power optimizers, and we have battery inverters as well. So central and string inverters are basically the same thing. The difference is, like for string inverters, for every solar string, like you have some solar panels connected in series. For every string, you have a inverter, dedicated inverter there. But in the central inverter, it is different. You have so many strings connected together, which comes to a combiner box, and the single output is given to the central inverter. So central inverters are usually used in industrial kind of stuff, which is high power, or even in solar farms, which generating power for the grid as well. String inverters are used in some part of industry, and mostly it is used in residential usage. Okay, then we have micro inverters. Micro inverters are the latest trend in inverters. Like first you saw that, like for the string, for the series of panels, we have one inverter. But in micro inverter concept, you have one inverter for each panels. Each panel will be installed with an inverter, which is called micro inverter. Usually micro inverters are very low in power. Like if you have a 200 watt solar panel, then 200 watt micro inverter would do the job. So it is low, very low power rated. But the advantage of micro inverters is, let's say that you have this kind of arrangement for solar panels, and there is a shadow or there is some dirt on one of your panel, and then efficiency of that panel will drop. So I don't know whether you are aware, there is a algorithm running like maximum power point tracking in inverters, which is to the algorithm which runs to get the full power from the solar inverter at a given point of time. Like it extracts the maximum power which is available at the moment from the solar panel. So it's running that algorithm. So when there is a drop in one panel, it totally affects the other panels as well, because everything is running on single inverter. So when there is a drop in one panel, it is affected the other panels as well, and total efficiency is dropped. In solar, even in all renewable energy, what is important in efficiency? Even for electric vehicle, efficiency is the most important thing. Those are the numbers which you can show what you can perform with your converters. The more the number, the better the product. So in micro inverters, when there is something like shadow or a dirt in a single panel, that affects only the that panel. So other three panels works with full efficiency, 100%. So when we are comparing the both converters, efficiency is high in micro inverters, but that comes with a cost. Like here, you just need only one converter, but you need 4 converters. But those are small in size. Still, you need 3 inverters there, and you have to install it to each panels. So those are some drawbacks of micro inverters. But I don't think that is important when we compare, when we talk about efficiency. Okay, then we have power optimizers. This is just like a mix of string and micro inverters. So if you already have a string inverter and you want to overcome that problem, then you have these micro inverters, power optimizers. Power optimizers doesn't convert the solar voltage into an AC or grid voltage. What it does is, it extracts maximum power from each panel and converts it into a DC. Like a maximum power point tracking is done on that particular device. So it already extracts the maximum power and send it to the bus. When it sends to the common bus, drop in single panel won't affect the other strings. So if you want to integrate the microinverter concept into existing string inverters, you can use power optimizers. It is market available. It is already in the market. Those kind of stuff can be used to increase the efficiency in inverters. Okay, then we have backup battery inverters as well. This is some photo I got it from SMA, one of manufacturers. So battery inverters are like, this is not used alone mostly. Some people use it alone. Like even the SMA manufacturers, they manufacture battery inverters separately. So you have a battery pack, and then you have to, without even solar or even during the night time when you want to power, you can use the battery inverters, which is same like the concept we use in the car, like changing it into AC. So then we have hybrid inverters, which is the combination of solar panels and battery. This one also you can find it in the market for a long time. Like most people are willing to buy this stuff now. So what is advantage of this is battery and solar panels are integrated together. During the daytime, most of the power is absorbed from solar panels, and after it is supplied to the home usage. If there is excess, it is fed to the grid. First it's fed the home requirement, and then it is used to charge the battery. Like in the daytime, it charges the battery. And if there is excess, even after charging the battery, it is fed to grid. During the night time, you can use the power in battery. So you don't have to pay any electricity bill or anything. Even you can deliver power to the grid as well. So during the daytime, using it from solar panels. During night time, you are using it from battery. As of course, you don't have to pay for power from grid, but there is an initial investment with solar panels and battery, but that will be comparatively less than the electricity bill. Okay, even in hybrid versions, there are two batteries, like high voltage and low voltage batteries. The future is like just like cars, even solar inverters are equipped with high voltage batteries like 400 volt, 500 volt batteries. 400 volt, 500 volt batteries, but still they are using 48 volt batteries as well. In Sri Lanka, most of the backup systems used are low voltage systems like 48 volt battery systems. But we have high voltage battery systems in the market as well. Okay, there are some questions in the chat. I will answer those questions at the end of this session. Okay. Okay, that's it about a small introduction about how power electronics is used in electric vehicles and renewable energy. I mainly spoke about solar inverters in renewable energy. Now we'll talk about switching devices and the trend, how it's developing and what's the future of it. So switching devices are like the most basic and important device in an power electronics, converters or inverters. So actually it started with a mercury arc rectifier. That was the first Dc2 Dc rectifier, which was developed in I think early 19th century or something. I can't exactly remember the date. So this is the timeline of development of switches. First they came up with thyristors, and then you have triacs, BJTs, and then you have gate turn-off transistors and MOSFETs, and all the others are like MOSFETs, IGBTs. Those are even used today. Those came after the invention of triacs and BJTs. And now what we have is wide band gap technologies. That is the most hot topic in the power electronics market now. That is like wide band gap materials are like silicon carbide, GaN like gallium nitride. Those, instead of silicon carbide and gallium nitride are taking over the market. So those are the trending technologies now in the market. I will talk about those technologies in later slides. So these are the four kind of switches mostly used in power electronics, like IGBTs, silicon FETs, silicon carbide FETs, and gallium nitride FETs. Okay, so where can we apply these devices? There are so many devices, and how the change of application. So this is just a overview idea how these devices are used in different power domains and frequency domains. Actually, IGBTs can handle high power, like they can handle high currents, voltage, but they can't be switched in high frequencies. So for high power applications, like more than 100K or something like that, you can use IGBTs, but that's the ideal solution for high power things. But on a drawback with the IGBTs are you cannot switch that in high frequencies. And that's the leftmost one. And then you have GaN, that is gallium nitride, that is wide band gap devices. In that, that's the high switching device. Like you can switch those devices in very high speed. So the drawback still with the GaN is you can't handle high power. There are limitations with power. So it is still under development. So I hope in future they can catch up with some medium power level or even high power level in the future. In between, you have silicon MOSFET and silicon carbide MOSFETs. So difference between silicon and silicon carbide is like relatively silicon carbide can handle high power in high frequencies as well. Usually the ratings of silicon carbide is more like 900, 1200 volts. So those are found in very high voltage ratings. So silicon carbide can be used in high power applications as well, while the MOSFETs are used in low and medium power levels. Okay, you might wonder what's the special with GaN and why it can be switched very fast and why it is trendy. So these are some reasons, like lower on resistance. I will talk about it in next slide. So what does that mean in a surface level? And it has very less switching losses. Losses are more important. As I said before, efficiency depends on losses. And you have less capacitance. Let me talk from the picture. That will be easy for you. So this is the comparison of on resistance. So MOSFET is just like a switch, used like a switch in a power electronic converters. So when it is on, it should act as a pure conductor. There shouldn't be any resistance. Ideal MOSFET should act as an 0 ohm, 0 ohm when it is switched on. But in real world, there is a resistance between drain and source. If there's a resistance, there's a power loss. So that resistance should be reduced to reduce the power loss. So in this graph, you can just see in the y-axis, you have on-state resistance, which is very low for GaN, very high for silicon, and it is in between for silicon carbide. So how it is beneficial is on-state resistance reduces the conduction loss. So when MOSFET is conducting, loss through the MOSFET will be very less. Heat produced by the MOSFET or FET is very less. So you can save energy there. So that is the main use of very low resistance. And then we have capacitance. So even we have just symbol of MOSFET, this is the actual MOSFET equivalent circuit. You have a capacitance between gate to source terminals of a MOSFET. So I'll just say like a MOSFET is a 3-terminal device. You have drain, source, and gate. You have to give some voltage in the gate to switch on the MOSFET. And you have to bring down the voltage to 0 or negative between gate to source to switch it off. So I just gave some basic function of the MOSFET, so I can explain this stuff. So actually what happens is you have to charge this gate to source CGS capacitor to switch on the MOSFET. That is what's happening inside the MOSFET. So if that capacitor is less, you need less time to charge that capacitor. So turn on time will be very less when capacitance is very less. So that saves switching loss. Like switch on time is reduced. So the power loss or heat loss during the switch on time is reduced. in that configuration. So this is just a comparison from a company called Visaysi, which primarily develops GaN devices. So this is what they came up with. Like they claim that their power loss is very less comparing to other manufacturers and also comparing to silicon carbide power loss. So you can see here, according to this graph, for the same circuit, silicon carbide dissipates around 900. GaN dissipates around only 200. It's almost 4 times savings. So that is the very basic, very interesting use of GaN. Another very interesting use of GaN is compactness. So I spoke about high frequency switching, like GaN devices can switch very fast. So you might wonder what's use of switching very fast. So when things are switching very fast, the inductance like filter circuits or transformers, what you need is very small. Like you don't need bulky inductors or transformers. So everything can be compacted. So this is the evolution of chargers. Like you have a very big same rating, 65 watt charger. This is how it's changing. 65 watt. Then you have like they might have used silicon carbide or something. Then you have very small one and also a fast charger. That is comparatively very small evolution. Okay, this is another interesting example. Like on the left picture, you have a circuit made with the silicon devices, and in the right side you have a device, like not the rightmost photo, middle photo is something made with the silicon carbide. So both the circuits are same, but you can see the size is very small. The inductance are reduced, even capacitors. So that's the major advantage of going into the GaN. And also another thing is, if there is less power loss, what you can see is you don't need complex thermal management systems. So if you see even in our car, in everything, the thermal management is challenging. You have complex thermal loops. You have to make cold plates to cool the stuff. So you need separate cooling lines running for it. So with the GaN, you can just, as the heat is very low, the dissipated heat is very low, you don't need bulky heat sinks. You don't need, even you can cool the stuff without external cooling loop or something. You can cool it with natural cooling, like air or something. So that is one main cost cutting of GaN. And here I have showed a picture of onboard charger, which is developed by Visaysi, which I mentioned earlier. This is actually a size of a small exercise book. The inverters, which is this onboard charger, which is found on nowadays vehicles, are very big. Like you don't find it in the exercise book size. This is the R&D development they have done. It is like very compact, and you can see it, like you can save a lot of space in the car, and it reduces the weight of the car as well. Another good thing is, like I said, GaN devices are very compact. Like they can block high voltages even in small gaps. So this is just comparison of MOSFETs and GaN of same ratings. The top ones are MOSFETs, and bottom these small devices are GaN devices. So in that case, you can see a lot of space in PCBs, like printed circuit boards. When the components are very small, you don't need like a big PCB or big placement problems, those kind of stuff. Okay, that's a pretty brief introduction about GAN. And as devices are developing, what is challenging is that even what we are facing now is designing the PCBs for power electronics is very challenging. Like you have to consider about the trace speeds, inductance in the PCBs. So when you are going for high frequency switching like GaN or silicon carbide, those PCB inductances become significant. So what manufacturers do, even for the silicon carbide, is like they try to integrate the whole thing into a module. Like they put the MOSFETs, drivers, everything into a pack and they deliver the solution. So that reduces the time to market. You can just take a module. You don't need any MOSFET drivers or anything. You just have to give the signal for microcontroller. I show some examples. This is one of the IGBT module example from Semicron. So here what they have is the black one on the bottom is the IGBT. That is just one IGBT, high power IGBT. So that is a half bridge configured, not just one IGBT. They have two IGBTs, which is connected in series. That is what we call half bridge configuration. They provide the whole solution. They packed it and they provide the driver board as well on top. So it simplifies our development and it simplifies our design as well. So what is in previous devices, they just integrated the half bridge into one single module. With the GAN, what they do is they have integrated even the gate driver circuit into a small chip. Like this is from Texas Instruments. So inside this small chip, they have 600-volt switching device and the driver for it. So you don't have to worry about PCB trace or PCB inductance, nothing. You just have to get that device and solder it and do your development. So it reduces a lot of time there. This is the latest development with the GAN technology. There's another manufacturer called GAN Systems. They developed far advanced systems like the half bridge. The whole half bridge section is inside a chip, a small chip. Like you have two MOSFETs and you have driver for both of them inside a single chip. So it reduces the time comparing to this single driver. So this one you have two switches, two drivers, everything inside a chip. This one reduces our development time by a lot of time. Okay, that's trends in switching devices. So just we'll talk about market penetration. Like in 2018, predominant market share for onboard charger is silicon-based silicon IGBT module onboard chargers. What you find in the electric vehicles are based on IGBTs. What they forecast is, like in 2018, GaN and silicon were under development. And what they predict is in 2025, the silicon MOSFETs will have significant market share with IGBTs. Like there are a lot of researchers, like a lot of universities are doing a lot of researches on that. And even the car manufacturers are doing a lot of researches. So silicon carbide will take significant market inertia in the future. And by 2035, the use of IGBT will drop and silicon carbide will take the predominant market. And along the line, GaN will take over silicon MOSFET, and GaN will be used in almost everything in the future because efficiency is everything. Like when you're converting power, nobody likes to lose any of it. So finally, what is important is efficiency. So this is the market of GaN in other areas. Like now you have even mobile phone chargers and stuff coming with GaN devices. The small chargers which you see are equipped with GaN devices. And now there are development with electric vehicles, which you can see in coming years. Like you can see GaN, onboard chargers, traction inverters, DC-DC converters and all. And in 2030, it will take over industrial markets like data centers, power supply for UPS, and those kind of stuff. Okay, that's it about power switching devices. I'll just rush through some of topologies like which I think trending now. These are some conventional DC-DC converters. Like as I said in the start of conversation, DC-DC converters are like converting DC power into another level of DC power. So these are some conventional ones. So one interesting topology is like LLC resonant converter, which is used mostly in DC-DC converters. So as I said before earlier, efficiency matters. So this has very low switching losses. Like if it's interesting, just read about LLC resonant converter. It has a concept called zero current, zero voltage switching, which reduces the switching loss very much. So this is the one of the interesting topology in DC-DC converter. And then you have interleaved DC-DC converters, which reduces the output current ripple mostly. This is just a development from conventional boost converter. You just have another branch there. So this actually improves current ripples. You get a very low current ripple when you supply it to the load. Those are like just two topologies. There are other topologies, interesting topologies, which is found in the research. And this is the inverter. This is DC to AC. These two are, I think you might be aware, a full bridge inverter and a half bridge inverter. Those are very basic ones. But what is trending in the market now is multi-level inverters. Like there are three kind of multi-level inverters: diode clamp, capacitor clamp, and cascade. So what is interesting about these multi-level inverters is you get the smooth output, like smooth sine wave when converting. So the first picture you have is conventional one. Like you have a half bridge or full bridge inverter. So those have only two levels. So you have to make sine wave only with two levels. So the smoothness of the sine wave is not accurate. The second picture you have is using a 3-level inverter. And the third one you have using a multi-level inverter, like I think it's 5 or 6 number of levels. So when the levels increased, you get a smooth waveform. That also helps in reducing the harmonics as well. So these are some examples of multi-level inverter topologies. This is using 8 switches. One drawback using these technologies is you need more devices, more switching devices, and complex algorithms. Those are the drawbacks. But overall, these inverters are high efficient. Okay, the another one is AC to DC thing. These are very basic one. First one is just a bridge rectifier and active rectifier, which we used in most of the circuits. The interesting ones are like Viana rectifier. It is an interesting topology. These are mostly used in onboard chargers, even electric vehicle charging stations in front. Like it can do both. It can boost the voltage, like boost the AC voltage to a DC value, and also it can perform power factor correction simultaneously. So both of the things are done in same algorithm and same converter. There are different configuration even inside the Viana rectifiers. And then you have Totem pole rectifier. This is also one of trending technologies now. This also can do both boostings and PFC as well. Even nowadays, even there are totem pole rectifiers. They don't use diodes D1 and D2. They use even the MOSFETs there to reduce the switching, reduce the conduction loss there. So those are the some basics of topologies. So that's what I prepared for today. I hope it helped. Let me check the questions on the chat if I can answer them now.
Yes, guys, if you have any more questions, just feel free to unmute yourself or just drop it on the chat box.
Someone has asked the first question was, can you share the slides with us? I will check on with that. Like I can share the power electronic stuff, the company stuffs. I think most of them, I think I cannot share the company stuffs. Other stuffs, I will be able to share that. In electric vehicle, are they using 230 volt AC motors or 3-phase? Most of the time they are using 3-phase motors, but not 230 volt. It is varying. It's a 3-phase motor. What is the voltage of battery used in electric vehicles to drive, and do they maintain a separate 12 volt battery for other operations like light? Yes, usually the electric vehicles use 400 plus voltages. There are like Mahindra's Mini, with those uses very low voltages, but the averagely the voltage is around 400 plus voltages. Yes, definitely there is 12 volt battery for auxiliaries like headlights, source, and other small stuff. So as I said earlier, there is a converter called DC converter inside the car, which is used to charge that 12 volt battery. So those 12 volt batteries are charged by high voltage batteries.
So I can remember you mentioned about 48 volt batteries also.
Yeah, like 48 volt batteries. They are developing, like the new vehicles. Some vehicles even have 48 volt. Like for, I can't exactly say which vehicles. Like some vehicles use 48 for air conditioning and stuff. And in future they are planning to change everything to 48 volt. That reduces a lot of wire harnessing. Like when voltage increases, you have to handle with low current. So the harnessing, that wire thickness of the wire reduces a lot, and you have very low power losses. Do you use a computer system to control the power conductors? No, actually, I don't understand what you mean by computer system. We use microcontrollers to control the power converters. Every algorithm is run on a microcontroller. We get the feedbacks like voltages, currents, and temperature from the device, and run the algorithm in the microcontroller and give the PWM to the switches. So we definitely use a microcontroller there. What is the DC-DC converter topology used in VEGA? So I'm afraid that I cannot answer technical things related to VEGA due to company policy, I think. So that's it on the question. The next question is also same, like how many levels are there in VEGA's multi-level inverter? So I can say that we are not using multi-level inverters at the moment. Our development, like the current motor control doesn't have multi-level inverter. Future, like what we are developing now for the future of the car will be based on multi-level inverter. Most probably will be 3-level inverter. So we'll start with 3-level inverter. Why are certain chargers built by companies charge their EV faster using fast chargers, but those fast chargers doesn't support other brands? Is it designed in a manner to support only their brand, or it is how? Sorry. Why are certain chargers built by company? Is it designed in a manner to support only their brand, or is it how the technology works? I think it is just like a question on like.
Can I clear it? I just took it out from how the Tesla system, the network works. So
Okay.
if you when you compare certain chargers from Tesla, their fast chargers doesn't support like chargers of other companies. Is it because they are like want to grab the customers to their brand so that they have a good supporting charging systems? Then it's common. It's not only test price. If whatever brand you take, their fast chargers support only their brands. So like being a company like you, so if when you're selling to a like company in India, so how do you like integrate that to their brand?
Like as you said, those are for marketing purpose. Like they usually compatible with their own cars, so it doesn't support the others. But our chargers are what we are developing is for the standards like CCS, charging, or that standards that the IEEE or the standard companies, they have a different charging standards. Sorry, they're not different, common charging standards for every vehicle. So our chargers can charge those ways almost like we have developed for 5 or 6 brands. I can't remember the exact number. So, but our chargers can charge all the vehicles. Our chargers are developed according to the standard mentioned by the IEEE. So our chargers can support even Indian vehicles. We test it here. Whichever the vehicle which follows that procedure like CCS or charging or any other protocol, our chargers are compatible with that.
Okay, thank you.
Okay, then what are the softwares you used for motor controller, inverter, ECU, battery controller, circuit designing? Also, what are the programming? Yeah, and also I think this is more into a company kind of questions. I can answer the general kind of questions. I'm not authorized to answer anything related to the technology related to VEGA or like any softwares we use. That is like we can't disclose that. How do you cool power electronics in VEGA? Yeah, we have a separate cooling loop running. We have radiators as in other vehicles. We have cooling fans as well. And we have coolant running across the power electronic converter. Like when you make the power electronic components, when the heating elements are like MOSFETs or IGBTs and some inductive components, those things will be fitted to the cooling pad or heat sink. So those cooling pad will have a thermal loop, like they will have a pipes inside them integrated, which runs the liquid inside them. So it is a liquid cool technology. That is how we cool, like liquid runs through the converters and battery packs, and then it goes to the radiator, and then it cools down there. Is that efficiency of the battery in electrical car reduces when we are operating headlamps at night? Is that efficiency of the battery in electrical cars? I can't exactly answer this, but according to my understanding, I don't think there will be a loss in efficiency, because efficiency depends on the converter thing. So the converter overall efficiency might not get affected, but maybe there is some part of power is given to headlamp. There might be some reduction in the power to the motor controller or something like that. That's what I can answer now, according to my knowledge. What is the project year of release of your electric three-wheeler? How much have your charging centers have been used within in Sri Lanka? Does VEGA Innovator offer internship, and how could someone apply for internship at VEGA? So our electric three-wheelers we are planning to market by next year, mid of next year. And also our charging stations, I think we have around 500 or 600 plus slow chargers. I can't exactly remember the number. And we have a good number of DC chargers as well. I don't have the numbers with me, but we almost have chargers around the island. Does VEGA Innovation offer internship, and how could someone apply for an internship? Yeah, when you're applying through the university, so your batch representative or your course coordinator can contact VEGA, and they can ask on the vacancies available, how many internship they are offering. So they can collect the CVs and send to us. We will have interviews, and definitely we'll get few of them for our internship. So we have been giving internship to all the universities. Yeah, that's how you have to apply for it. So we don't call it in an advertisement. It is mostly through universities. And the next one is, what are the switching devices used in VEGA power electronics? What is the microprocessor used in VEGA ECU? Okay, the first question I'll just answer in overall manner. It applies the same what I said earlier. So I will say we are using the IEEEs now, but microprocessor, like as I said earlier, that is more into technical stuff, so I cannot answer it now. Why does the car require 12-volt battery? Why can't high voltage battery be used with the Dc2 Converter electrical power 12-volt system in the car? It is the car. Okay, as I understand, what you're asking is like you are saying to directly power the 12-volt, directly power all the auxiliary with high voltage, right? So high voltage is not always powered, like when you park the car or something like that. Even though high voltage is switched only when you need it. So when you don't need the high power, so the system runs on 12-volt battery. So there should be a 12-volt battery running to run the auxiliary systems like ignition or headlight or some basic stuff which you run without without high power. And also there's a concern of efficiency. So if you run all the auxiliary with 12 volt with direct DC, then there will be a lot of power loss, like it has to work every time. So when the energy is once stored in the battery, I think that is more efficient way to do that. Can a level 1 charging car be charged by a level 2 charger using an adapter on the Topologies? According, I think level 1. Is this question is about like AC charger and DC charger? I don't understand like level 1 charging and level 2. I would meaning like AC charger and DC charger. Or if you are meaning that, then you can't charge it using an adapter. The topologies are totally different. The DC charger directly goes into the battery and AC goes through the onboard charger. For vehicular communications, what protocols you use? Example, CAN. Why don't you use DC motors? Why don't you use DC motors for VEGA? Okay, for vehicular communications, we use CAN. That's what we use in VEGA. Why don't you use a DC motor for VEGA? Yeah, maybe I'm unable to answer that question now. I will skip it. Which vehicles are more powerful in terms of power? Is it fuel vehicles or electric vehicles? So actually, it doesn't depend on fuel or electric. It all depends on the engine and the motor control power. So it is like how in electric vehicle, how good you develop your power electronics. So the power depends mostly on the development side, not really on the fuel or electrical side. I'm going to use solar power as a source to charge in 3-wheelers. Yes, of course, not primary one. We are going to use solar power to charge 3-wheelers, like when they run or when they park in the noon time, something like that. But we definitely will have a charging socket there to charge their batteries in our charging outlets. That's it for that. Do EVs have transmission? Yes, they do have gearbox. Yeah. Okay, that's it from the chat box.
Excuse me, sir, I have a question.
Yeah.
Sir, you said that VEGA is planning to introduce the new electrical three-wheeler into the market in recent future. So with this kind of projects, does VEGA has any plans to develop the currently existing charging infrastructure in Sri Lanka?
Yeah, like definitely we are already developing our chargers. Like comparing to the last few years, we have developed a lot in our charging infrastructure, and we have even plans with our chargers in like light lamp poles or charging parkings and those stuff, small chargers for electric 3-wheelers and stuff. So definitely we will be developing the charging infrastructure for electric 3-wheelers as well.
Okay, sir, thank you.
Excuse me, sir.
Yeah.
When we are using micro inverters with solar panels, like
Yeah.
we'll have to use a micro inverter for every panel.
Yeah.
So then when there is a defect, how can we identify the exact panel with the defect in the micro inverter?
So like the whole system is like when there is a fault, it fires the error. Like in nowadays solar inverters are integrated with mobile apps or web application or anything, and they have software. So like they have Wi-Fi connections inside that. They will be uploading the data to the cloud or something like that. So when there's a defect with some micro inverters, it fires an alarm for your mobile app, your web interface, saying that this particular micro inverter is defective. Or even I think even you can see some visual changes, like they might have some lights indicating the fault. So that's how it is detected.
Thank you, sir.
Excuse me, sir.
Yeah,
Excuse me.
yeah.
Are VEGA planning a car for general customers?
Yes, we are planning on that, but not immediately. But we are planning that on near future. We'll be working on it in near future, but not immediately.
Okay, sir. Thank you.
Okay.
So we had quite a lot of questions. So actually, I have my question. I have my own question. Like from the recent events, like yesterday, we had a blackout. So I should ask, like integrating power, like vehicle charging systems, would it affect the system? I don't know whether it's out of the scopes of power electronics, but do you have any idea?
Definitely the demand will increase, right? So when you put chargers and so stuff, definitely demand will increase. So the power generation, this has to be compensated with power generation, or we have to go for renewable energy kind of stuff, like they have put up some power in now, or they can even, that's what I say, that we are planning something in future with no grid connection, like with solar panels, we are charging our DC chargers, something like that. We are planning in future.
Thank you, sir. So do you guys have any other questions?
Okay, if there are no questions, then okay, thank you for this opportunity. It was great talking to you all and answering your questions. Thank you.
Sir, thank you, sir, for your knowledge sharing and inculcating many inspirations within our hearts. Thank you, sir. So, with our utmost gratitude, it's my pleasure to present the token of appreciation for helping us to nourish our engineering student career. Mr. Prashanth Atputhakumar, please accept our token of appreciation.
Thank you. IEEE Power Energy Society of University of Ruhuna. Thank you.
All right. So as we are reaching the end of our session, it's my pleasure to invite our Vice Chair of the student branch, Mr. Piyumar, to deliver the vote of thanks.
Good evening, everyone. On behalf of the organizing team, it's my privilege to present vote of thanks on this session. First of all, we are really grateful and thankful for our distinguished guest speaker, the head of the power electronics at VEGA Innovations, and not only for sparing his valuable time, but also for enlightening us with his vast knowledge in power electronics. And also, I would like to extend my sincere thanks to all the participants who was with us for this webinar. And thank you very much.
Okay, thank you, Piyumar.
Okay.
So, thank you, sir. So this is the ultimate of our session. So I'd like to invite all of you turn on your cameras to take a photograph. It's the main of this occasion. Guys, anyone who feels free to turn on your cameras, just let's turn it on. Let's take a photograph. So I'll just count to 3. Okay. 1, 2, 3. Say cheese. Okay, thank you, everyone. Thank you, sir.
Thank you. Have a good day.